Good day, everyone. So today we shall be considering a topic titled Gravitational Field. Gravitational field. Okay, among the three types of field we have, gravitational field is the only one that we say have just one direction of force. All right. Of course, we have other field like electric field, magnetic field. Okay. But gravitational field has only one direction of force, that is attractive force. So let's dive into this topic, gravitational field. Okay. Now, by definition, gravitational field is a region or space around a mass in which the gravitational force of the mass can be felt. So when we talk about the field, it's just a space around an object. When we say mass is an object that exhibits such kind of force, because the field itself is the type of force. So when you have an object, that object generates a force, and that force is generated is called a field. In this case, we call that force the gravitational force. So we say it's a region around the mass in which the gravitational force of the mass can be felt. All right, and gravitation itself is the force of attraction exerted by a body on all other bodies in the universe. Look at this object here. That ball represents the Earth. You can see those square boxes being attracted to it. That's because the Earth is generating a gravitational field that is attracting all other bodies around it. Okay, that is what gravitational force is all about. It's just a region or a space around the mass that generates this force and attract other force. So it usually exists between two or more bodies. The galaxies, the planet, the star that we have are all bound together by this gravitational force. And each of these objects have their own gravitational force. Okay? Now let's talk about the law that guides this gravitational field we are talking about. That law is known as Newton's law of universal gravitation. Newton's law of universal gravitation states that every particle in the universe attracts every other particle with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between them. Okay, what is this law saying? By those statements you have there, it means that in the universe, if you have two masses being attracted together by a gravitational force, the force attracting them together get increased as the distance between them gets reduced. That is what the law is just saying in the layman's language. That every particle in the universe attracts every other particle with a force that is proportional to the product of their masses and then inversely proportional to the square of the distance between them. So if the square of the distance between them is smaller, then the force of gravity will increase. Okay, let us see an instance in this law. Look at this. Simulation. Now, bringing the distance, measure the distance between M1 and M2. Look at it. Here now we have, let's say we have 4.6 meters distance between M1 and M2. Now look at the force acting on them. We have a force of 1.26 times 10 to the power minus 7. But by the time we now reduce the distance between them, you can see that the force of gravity between them has now increased from that value to 1.95 times 10 to the power minus 7. That is to tell you that the more you reduce the distance between the two masses, the more the gravitational force. And the more the distance between them, the lesser the force. So when the distance between them is smaller, the force between them increases. But when the distance between the two masses is bigger, then the force between them reduces. That's what Newton's law of gravitation is saying. Okay, so let's go back to what we're talking about. So we could see that F, which represents the force, is proportional to the product of their mass. That means if you multiply the mass together, the higher the value, the higher the force that is acting on them. So the product of the mass, m1 and m2, and inversely proportional to the square of the distance between them. The capital G there represents universal gravitational constant, and the value is 6.67 times 10 raised to power minus 11 Newton meter square per kilogram square. So this is a constant. It's a constant that has been derived from the laboratory that it happened to be this value. All right. So moving on, we need to talk about the gravitational field intensity. Gravitational field intensity. Now, gravitational field intensity at a point is the force per unit mass of an object placed at that point. Okay. Now, the force that is acting on 1 unit mass of an object is known as gravitational field intensity, and it is represented with small letter g. So by formula, we say G equals to what? F over m, where the F represents the force acting, the gravitational force acting on that object, and the m represents the mass of the object. Then by unit, the unit of gravitational field intensity is Newton per kilogram. Okay. So very key. And it is a vector quantity, meaning that it has magnitude and direction. Also note that this gravitational field intensity is also called acceleration due to gravity, because we are dealing with what? Gravitational force. So it's also known as what? Acceleration due to gravity. All right. Now let us now look at the relationship between small letter g and capital letter G. Recall that small letter g is known as what? Gravitational field intensity, or sometimes called acceleration due to gravity. Okay, why the capital G is known as what? Gravitational constant. Okay, universal gravitational constant, and it has a value as well. Now we want to see the mathematical relationship between them. Now recall from Newton universal law of gravitations. By the formula, we have F to be capital G m1 m2 over r squared. Recall again that we said that gravitational field intensity by formula is equal to F over m. Now we need to pick any of the m. Now I'm picking m2 now. So we have two equations now, equation 1 and equation 2. Now equation 2 can be expressed as G equals F times 1 over m squared. So this one can also be expressed in this way, F times 1 over m squared. Still the same thing. Why we are doing this? Because we want to show the relationship between G, capital G and small g. Now, having made equation 2 this equation, making equation becoming equation 3. Now, we now have small letter g in equation 3 to be F times 1 over m2. Now, if we substitute value of F in equation 1, this is equation 1 here. If we bring this value into equation 3, now where the F is now, we are going to replace it with its value, which is g m1 m2 over r squared. So that will now give us small letter g. This g here equals, instead of writing this F, we are substituting its value, which is g m1 m2 over r squared multiplied by 1 over m squared. Okay. Now 1 over m2 rather. Now m2 here cancel this m2, and then we are left with g m1 over r squared. So this shows the relationship between small letter g and capital letter G. That is, small letter g equals capital letter G m1 over r squared. So if you are told to show the relationship mathematically between acceleration due to gravity and universal gravitational constant, this is just how to go about it. All right. So that's it. Now, having said that, let's talk about another concept again, and that is known as gravitational potential. Gravitational potential. Gravitational potential at the point is the work done in taking a unit mass from infinity to that point. Okay, so this one is talking about work done. The work required to take one mass from infinity to the particular position the mass will be is called the gravitational potential. And by unit, the unit is joule per kilogram or J kg per minus 1. By formula also, we say that gravitational potential is equal to, we use V to represent it, equals to minus capital Gm over R. While the G still remain the gravitational constant, the M is the mass of that object, and the R is the distance from the infinity where the mass is to the new position of the mass. Now, the negative sign you are seeing there shows that the the potential at infinity is higher than the potential of the object at its new position. So that's what the negative sign represents. So potential at infinity is always higher than the new position. All right. So the next thing or the next concept about this gravitational field is known as the escape velocity. The word escape, when you are trying to, save yourself from a particular danger. Now, escape velocity simply means the minimum velocity required for an object, such as satellite or rocket, to just escape or leave the gravitational influence or field of an astronomical body permanently. If this satellite or rocket do not leave this gravitational influence, there is no way they will remain outside the planet. So now that minimum velocity required by this object is known as escape velocity, and we are going to derive the formula for it. Now recall that we use capital M in this topic to represent mass of the Earth. We use small letter m to represent mass of the satellite, and then of course the G still remain what it is. Again, going by the formula of gravitational law, it says F equals to G m1 m2 over r squared. In this case, our m1 is capital M and our m2 is small letter m, then over r squared, which is the distance between them. Okay, now the work done in carrying a mass from a point through a distance r from the center of the earth is equal to G capital M small m over r. Take note of that. So this is the work done in moving an object from one point of the center of the earth to another point. So it's G capital M times small m over 1. That is another key equation you have to know. Now, for us to obtain our escape velocity, we then need to also know our kinetic energy. Kinetic energy is energy in motion. Okay, now the kinetic energy formula is half mv squared. Now the v there represents our escape velocity. That's why we have it as ve. So kinetic energy is half mv squared. So for us to obtain our escape velocity, we need to equate work done by the object with the kinetic energy of the object, because the work to be done must be the kinetic energy needed to move. So half mv square equals to g capital M times small m over r. Of course, where this formula at my right hand side represents the work done and the one at my left side represents the kinetic energy. Now, if you make VE the sort of the formula in this equation, you'll be having escape velocity to be square root of 2 capital G capital M over R. This is another key equation. Now, we still want to obtain another equation for escape velocity, aside from this one we just obtained now. Now, we are going to assume that our R, which is the distance between the two objects, to be capital R, which represents the radius of the Earth, and our small letter m1, we're going to replace it with capital M, which represents the mass of the Earth. Now, doing this now, recall that from the equation of acceleration to gravity, we have it to be gm1 over r squared. Now, if we now replace m1 with capital M and small letter r with capital R for this equation, we'll be having a new equation to be g capital M over r squared. Okay, replacing m1 and r with capital M and capital R respectively. We have this. Okay, now in equation 8, if you now make our capital G in equation 8 the subject of the formula, we have our G to be small letter g r squared over capital M, this equation 9. Now, if we substitute the value of G in equation 9 into this equation 7 here, that's our VE. We'll be having our VE to be what? Square root of 2GR. So escape velocity can be either square root of 2gm over r or square root of 2gr. Any of them depending on the nature of the question. So at this point, we are going to be drawing the curtain. So thank you for listening till we see again. Bye for now.